Hi all. So in the last class, we have just introduced what is a linear vector space. And we have said that the concept of linear vector space is not enough for the formalism of quantum mechanics. We have to move towards the Hilbert space formalism. Okay. Now, before going to Hilbert space formalism, we have to introduce two concepts for you. One is called the norm of a vector, and the second is called the inner product. So norm of a vector is very simple concept. So norm of a vector is generalization of length of a vector. Okay. So suppose if you have a vector A in 3-dimensional space, so this vector usually we denote as it will have x component, y component, and z component. So then how will you find its length? So length of the vector is simply given by square root of ax square plus ay square plus az square, or more technically we can denote it as square root of a dot a. So that is the length of a vector is square root of the inner product of the vector with itself. Okay, so a dot a is nothing but the dot product or scalar product. So the length of a vector is square root of scalar product. Okay. Now this the scalar product is x square plus ay square plus az square. Okay, so if you are having a continuous notation, then it is possible to write x square plus ay square plus az square is sum over I equal to 1 to 3 ai square, where I equal to 1 to 3 corresponding to x y z, I equal to 1 corresponding to x, I equal to 2 corresponding to y, and I equal to 3 corresponding to z. So this is a very simple notation. Okay, so in very compact form, the length of a vector in 3-dimensional vector space is sum over I equal to 1 to 3 ai square, where ai is the ith component, all raised to 1 by 2. Now this concept we can extend to n-dimensional vector space. So if it is an n-dimensional vector space, then there will be a total of n components for the vector. Then the vector A will have many components, the first component, the second component, and third component up to the n components. Then what would be the length of the vector A? So here we'll not use the term length, we'll use the term norm. The norm of the vector A is simply sum over I equal to 1 to n ai square, all raised to 1 by 2. Okay, so that's it. Now here we have shown that this vector A as discrete elements. So A1 is one first component, and A2 is second component, A3 is third component, etc. Now instead of if it is an discrete component vectors, if it is a continuous component, then what would happen? So such kind of vector is nothing but functions. Okay, so remember, for n-dimension vector, or to define n-dimension vector, we need n components. So n-dimension vector A, we need n components, A1, A2, etc. up to AN. Then what about functions? What is a function? Can you treat the function as a vector or not? We have discussed in the last class that it is possible to represent the function as a vector. What is the function? F of x. A function will have a variable x. For each value of x, there will be corresponding value for the function. The f of x, a function defined with a variable. Now again, the variable can be more than one. It is not required that only one variable is present, and is not required that that variable must be a scalar. It need not be that variable that variable need not be real. It can be a complex. Okay, so a function defined with variable. Okay, for the time being we are representing only single variable x. Okay, for each value of x, there will be a value, a single value for function f of x. Okay, so that means this function f of x must be defined at all values of x. Okay, so all values of x means we have infinite points. Okay, so that means in order to define a function, we need infinite components. So in order to define a function, we need infinite components. So that means a function has infinite components. Then we can treat a function as a vector in infinite dimensional vector space. Is that okay? So we are going the other way around. So if you require n components to define a vector, then that vector is a vector in n dimensional vector space. So if you require n component to define a vector, then that vector is a vector in n dimensional vector space. Here we are required infinite components to define a function. So therefore, a function can be treated as a vector in infinite dimensional vector space. Is that good? Yeah, it's good. Okay, then how will you define the norm of a function? So we know to define the norm of a vector. The norm of a vector is simply the sum over I equal to 1 ai square all raised to 1 by 2. Okay, the norm of a vector is sum over I equal to 1 to n ai square all raised to 1 by 2. Then how will you define the norm of a function? So norm of a function f so this is usually denoted by a symbol double line. Okay, so norm of a function f would be square root of sum of square of its component. But now the thing is here in case of vector a, the components are discrete, a1, a2, a3, etc. But in the case of functions, the components are not discrete. It is a continuous component. So instead of the summation, we have to go for integration. So this would be integral. Instead of ai square, I have to represent mod f of x square dx. Okay, so that will define the norm of the function. Okay. Now, it is also we discussed that the norm can also be written as square root of scalar product. So that means the scalar product of the function f scalar product of vector with itself, isn't it? That is the length of vector A is square root of A dot A. So that means the quantity inside this bracket is the scalar product of function with itself. So scalar product of function with itself, we are going to denote a new symbol for it. Okay, so usually for vector we denote this symbol A dot A, but for functions we denote this symbol bracket open f comma f, the bracket closed. So this is a notation we are going to denote for the inner product. So or scalar product. So the scalar product is equal to integral modulus of f of x square dx. Okay, so we have defined what is called the scalar product. The scalar product is also known as inner product. Okay, so we have defined two quantities now. We have defined the norm of a function. The function is also a vector in infinite dimensional vector space. So norm of a function f or the norm of vector f, we can write as integral mod f of x squared dx all raised to 1 by 2. And the quantity inside the square root is the scalar product of the function with itself, and that is denoted by symbol f comma f, and it is known as scalar product or also known as the inner product. So inner product of function with itself is integral f of x square dx. So why we required mod square? Because this is a norm, is connected to the square of the norm, so that must be a positive quantity. So this must be a positive quantity because this is a extension of the length of the vector. The length of the vector is always positive, so the norm must be positive. Okay. Now suppose if your function is not real, suppose if the function is complex, then again the same definition can be introduced. Okay, for complex functions. The inner product f comma f is again integral mod f of square. So mod f of square we can write as f star of x, f of x dx. And the norm is this. So there is the scalar product all raised to 1 by 2. Okay. Now this scalar product or inner product has of great use for us. It is not only to define the norm of the function, norm of the vector, it is also required for many other things. Okay, so then we have to give some more time for the discussion of the inner product. Okay, so we can define, okay, here we have defined the inner product with itself between the same functions or the same vectors, but in general, we can define the inner product between any two functions. Consider two vectors f of x and g of x in infinite dimensional vector space. then the inner product between them F and G is defined as the inner product F comma G is equal to integral F star of X G of X dx. So not that the FF, the inner product FF, the inner product with itself is integral F star of X F of X dx. Okay, so here the first term is called prefactor and the second term is called the post factor. So we are taking the complex conjugate of prefactor and the original function of post factor. There is no complex conjugate is taken here. So the same analogy has to follow here. So if you're writing Fg, then the first factor, the first function is called the prefactor and second is called the post factor. And while defining the inner product, we have to take the complex conjugate of prefactor and the original post factor. So that is the definition of the inner product between two functions or two vectors of infinite dimension. Now, what are the properties of inner products? We can list down the properties. The first property, the inner product is non-commutative. That means inner product Fg is not equal to the inner product Gf in general. What's the reason? Because if you take Fg is integral F star of X G of X dx, and what is Gx? Sorry, Gf is integral G star of X F of X dx. It need not be same. Okay, but we can say that this Fg is equal to Gf complex conjugate. That is possible. That is this we can write. Okay, or the first expression we can write is integral F of X G of X or G star of X complex conjugate dx. Okay, so F star of X G of X can also be written as F of X G star of X star of X. So if you take complex conjugate again, then G star of X will become G of X and F of X will become F star of X. So that would be the F star of X G of X. Okay, so this is equal to integral G star of X F of X dx, or the complex conjugate, and that is nothing but the inner product Gf complex conjugate. So the inner product is in general non-commutative. Now the second thing is the inner product is distributive. That is F comma G plus H is same as F comma G plus F comma H. This you can prove it yourself. Okay. Only thing is you have to take the same definition. That is, what is inner product f comma g plus h is integral f star of x g of x plus h of x dx. Now expand it. We can take two integration. So one integration would give the inner product fg, the other integration would give the inner product fh. So it is very simple to prove that you can prove it yourself. And the third property, f comma c g, where c is some number, c is scalar. If c is scalar, okay, it can be a real scalar or complex scalar. So in general, we can call it as a complex scalar. Then it is simply c times f comma g. You can take c outside. Okay, so it is linear in the pre-factor, sorry, post-factor. Now the next is important. If you multiply the c with f instead of g, with pre-factor you multiplied it. So c times f comma g is equal to c star of f comma g. Linear with post-factor. So this means anti-linear with pre-factor. If you're multiplying the complex scalar with the pre-factor, then if you're taking outside, you have to take its complex conjugate outside, not that the exact number. So that is the difference. So these are the four properties of the inner product. So every inner product has to satisfy this condition. Okay, now finally we have to introduce one more concept, what is called the unit norm vectors. Okay, so a vector is called normalized vector or unit norm vector if its norm is unity. And when you get norm unity, the inner product is the square root of the norm is square root of inner product with itself, or I can write the inner product with itself is unity. Okay, so a vector is called a normalized vector or unit norm vector if its inner product with itself is unity. So unit norm vector or normalized vector. And the under condition is orthogonality condition. So in three-dimensional vector space, two vectors are perpendicular if its dot product is 0. So if you have two vectors, vector A and vector B, and if the dot product is 0, then we can say that they are perpendicular. Okay, so the orthogonality is the extension of this concept. So a two vector F and G are orthogonal if the scalar product, or we can call it as an inner product, or inner product between them is 0. So two vectors f and g are called orthogonal if f comma g equal to 0. So this is called orthogonality condition. Okay, so we have introduced two more definition based on the inner product. We introduced what is meant by the normalized vector. A vector is called normalized if their inner product with itself is one unity, or it is also called as a unit norm vector. And two vectors are called orthogonal if the inner product between them or scalar product between them is 0. Okay, so that is enough for us for the time being. So we have discussed in detail about the definition of the norm of a vector and the inner product of vector or inner product between two vectors. And we defined, we explained the different properties of the inner product. And finally, we discussed the norm, or the normalization condition, and as well as the orthogonality conditions of vectors. Okay, so that is enough for us. And in the next class, we'll introduce a few more new concepts. Okay, see you later. Bye.